Раз. Well, I'm glad to introduce our next speaker, Yakov Veryovkin from High School of Economics. He will speak on the Lie algebra associated with the lower central series of a right-angled Coxeter group.
Thank you. Before I start, I wish to express my deep gratitude to Viktor Matveevich for everything he has done for me, and congratulate him on the occasion of his 80th birthday, and wish him many more years of fruitful work. Thank you. My talk is the Lie algebra associated with the lower central series of a right-angled Coxeter group. Let K is a simplicial complex on the set M, where M is the set of numbers from 1 to M, and empty set in K. Any element of K is a simplex. Bolt XA is a sequence of pairs of spaces where AI is subspace of Xi. Given I subset M, we set bolt XA power I is a product of Y1 to Ym, where Yi is Xy if I is in set I, and AI if I not in I. Okay. The K polyhedral product of bolt is стоп. Сейчас, может быть, надо вот сюда сделать. Тест. Нет, так не надо, нет. Мне кажется, что слышат, потому что я говорю, и тут что-то говорится. Тут я точно не знаю. Все как было всегда. Okay, next, yeah? The K polyhedral product of bolt XA is union like this, where the union is taken inside XY cross XM. We have next notation. XA power K is bolt XAK if XI is X, all XI is X, and all AI is A. Also, we have notation bolt XA, XK is polyhedral product X with point, and we have also it notation. Okay. Let we have example. Let XA is circle with point. Then S1K is union like this, and this in M torus. For K M disjoint points, the polyhedral product circle K is the wedge of M circles. When K consists of all proper subsets of M, S1K is the fat wedge of M circles, and it is obtained by removing the top dimensional cell from the M torus. Okay. Next, for a general K on M vertices, we have that wedge is subset of S1K and subset of M torus. Okay. We have next example. Let X is R and A is Z. Then we have LK, RZ K. This, when K consists of M disjoint points, is a gate in Rm, consisting of all lines parallel to one of the coordinate axes and passing out integer points. For example, is M equal 2, we have gate from integer points. Okay. when K is the bound of M-1, the complex LK is the union of all integer hyperplanes parallel to coordinate hyperplanes. Okay. Let ball J is a sequence of M discrete groups, where all GI is non-trivial groups, and K is a simplicial complex on a set M. We have definition similarly polyhedral product. We have definition the graph product of the groups. This is GK is factor phi product of GK by these relations, where we have commuting GI and GG for all edges in simplicial complex. Okay. The graph product GK depends only on the one skeleton of K. We have example. Let GI equals that. Then GK is the right-angled arching group. We have this formula. RAK is factor phi group rank M by relation, by commutation relation GI GG equals GG GI for all edges from simplicial complex. When K is a full simplex, we have that right-angled arching group equals Z power M. Rank M. Okay, we have next example. G Z2, then that Kokster group. Different from right-angled arching group, that we have relations GI power 2 equals 1. Okay. We have theorem. Let we have right-angled arching group, then fundamental group of polyhedral product with point of circle isomorphic right-angled arching group. Both S1K and LK are aspherical if and only if K is flag. All higher homotopical groups of S1K isomorphic higher homotopical groups of LK, and fundamental group of LK is isomorphic to the commutator subgroup right-angled arching group. And we have similarly theorem for right-angled Kokster group. But S1K changed to RP infinity K. And LK changed to RK, where RK is polyhedral product D1 S0 K. This has name rational moment angle complex. Okay. We have example. Let K be an M cycle, the boundary of an M-gon. A simple argument with Euler characteristic shows that RK is homeomorphic to a closed orientable surface of genus like this. This observation goes back to 1938 fork of Kokstera. Therefore, the commutator subgroup of the corresponding right-angled Kokster group RCK is a surface group. Similarly, when a geometric realization of simplicial complex K is two-dimensional sphere, rational moment angle complex is a three-dimensional manifold. Therefore, the commutator subgroup of the corresponding RCK is a three-manifold group. Okay. first theorem, this theorem of Panov-Verevkin. We have right-angled arching group, right-angled Coxeter group, and the commutator subgroup of right-angled arching group is phi if and only if one skeleton of K is a Hodel graph, and the commutator group of right-angled Coxeter group is phi if and only if one skeleton is a Hodel graph. Okay. Part A is the result of Servatius, Droms, and Servatius. And the difference between part A and part B is that the commutator subgroup right-angled arching group is intuitively generated unless RAK is Z power M, while the commutator subgroup right-angled Coxeter group is finitely generated. Okay. Let G be group. The commutator of two elements AB given by this formula. We refer to the following nested commutator of length K like this, as the simple nested commutator of Qi1, Qi2, and Qik. Similarly, we define simple nested Li commutators like this. Okay. For any group G and any three elements ABC from G, the following whole width identities hold like this, where AB is conjugacy A with B. Let H and W is subgroups of G, then we define bracket H and V as the subgroup of G generated by all commutators H small, V small, where H from H big and W from W big. In particular, the commutator subgroup G of the group G is bracket G with G. We have definition lower central series of group G. For any group G, set gamma 1 from G like G and define inductively gamma K plus 1 from G as bracket gamma K from G with G. The resulting sequence of groups gamma 1, gamma 2, and other is called the lower central series of group G. Okay. If H subgroup G is normal subgroup, we will use the next notation. In particular, gamma K plus 1 is normal subgroup of gamma K. And we have the quotient group gamma K by gamma K plus 1 is abelian. Denote LK like this factor gamma K by gamma K plus 1. And consider the direct sum like this. Given an element AK from gamma K, we denote by overline AK its conjugacy class in the quotient group LK. If AK in gamma K and AL and in gamma L, then then AK commutator AKAL in gamma K plus L. Then the whole width identities imply that LG is a graded Lie algebra over Z with Lie bracket like this. The Lie algebra LG is called the Lie algebra associated with the lower central series, or the associated Lie algebra of group G. Okay. We have theorem that Cas homology of this isomorphic this direct sum for any K more or equal 0 where like this. Is a theorem for proof next theorem. Okay. theorem Panov and Verevkin. Let a right-angled Coxeter group corresponding to a simplicial complex K is RCK with m vertices. Then the commutator subgroup RCK has a finite minimal set of generators consisting like this nested commutators like this with conditions where I less j and more k1, k2 and other kl minus 2 and ks not equal I for all s, and I is the smallest vertex in a connected component not containing j of the subcomplex like this. We have corollary that the free abelian group H1RK is isomorphic this factor of rank like this and has a basis consisting of the images of the iterated commutators described in theorem above. Okay. Let J be a group with generators GI. The Cas theorem gamma k of the lower central series is generated by simple nested commutators of length greater than or equal to k in generators and their inverse. Let RCK be a right-angled Coxeter group with generators GA. Then the group gamma k is generated by commutators of length greater than or equal to k in generators GI. Okay. From this, we have that the square of any element of gamma k is contained in gamma k plus 1. Proof this. We use induction by on n. We use induction on n. Let A from gamma k. For k equals 1, we have A equals this product. If k more 1, then we have this product, where AI is this commutator or this commutator. And BI from gamma k minus 1. Let n equals 1. The case k equals 1 is obvious because gk power 2 is 1. And if k more 1, then A is BGI commutator or GIB commutator for some B from gamma k minus 1. For a BGI, we have this formula and see that in gamma k plus 1. And for GIB, we have a power 2 like this in gamma k plus 1. Suppose now the statement is proved for n minus 1. Let A like this and A power 2 is this product. We have this formula and first factor lies in gamma 2k, but gamma 2k is a subgroup of gamma k plus 1. The second factor lies in gamma k plus 1 as a conjugate to A1 squared by induction. The last factor also lies in gamma k plus 1 by induction, because this is squared. Okay. That if LRCK is a Lie algebra, associated Lie algebra, this Lie algebra over Z2. We denote by FLZ2 a free graded Lie algebra over Z2 with n generators mu I, where degrees mu I equals 1. For any simplicial complex K, we consider the graph Lie algebra over Z2 like this free graded Lie algebra over Z2 factor by commutation relation for all edges in a simplicial complex. LK depends only on the one skeleton of K, as in the case of right-angled Coxeter groups, it is more convenient for us to work with simplicial complex. Okay. We have proposition. There is an epimorphism of Lie algebras. Graph Lie algebra to associated Lie algebra. LRCK is, yeah.
Right from the indicators or from the number of variables in each indicator.
Я плохо, да. How construct any simplicial complex for any simplicial complex.
Each vertex in this simplicial complex is derived from the number of variables in each indicator or
Я плохо понял английский. На русском дублируйте вопрос, пожалуйста. Можно? Да.
Специальные контексты сейчас связаны с математикой.
Okay. I see your question. We have m vertices in simplicial complex and m generators for Lie algebra.
So we have m
Vertices.
So we have m vertex.
For each vertex, we have one generator for Lie algebra. Yeah. Just we can discuss this during the break. Okay, thank you. Okay, there is an epimorphism. Associated Lie algebra is a Lie algebra over Z2 generated by the elements Gi from gamma 1 by gamma 2. By definition of a Lie algebra, we have an epimorphism like this, where mu I to overline Gi. Since there is a relation bracket like this equals 0 for edges from simplicial complex in the Lie algebra, the epimorphism this factor throws a required epimorphism phi. But in fact, the homomorphism phi from the proposition above is not injective, and the Lie algebra LK and LRCK are not isomorphic. This distinguishes the case of right-angled Coxeter groups from the case of the right-angled arching groups, where the associated Lie algebra L from right-angled arching group is isomorphic to the graph Lie algebra over Z. Okay, we have example that this is not injective. But me next. This example with calculate and we have LCI for two disjoint points isomorphic graph algebra CI component factor by this relation, because this is not injective homomorphism. Okay. Proposition let K consist of two disjoint points, then LRCK isomorphic this factor by these relations, infinite relations, where A is bracket. Okay. Theorem of Panov and Verevkin. Let K be a simplicial complex on set M. Let right-angled Coxeter group be the right angle corresponding to K, and LRCK is its associated Lie algebra. Then L1 has a basis like this: G1 class and Gn class. L2 RCK has a basis consisting of the commutators like this with I less j for ij not h in k. And LCE has a basis consisting of the commutators EGG, where I less g for not h ig, and EGK, where I less j more k and I not equal k. And I is the smallest vertex in a connected component of subcomplex K IGK, not containing G. Okay, we have corollary for first consecutive quotients of the lowest for free product of the group Z2. Let K be a set of M disjoint points, and we have then right-angled Kokster group and is free product of M exemplar of Z2. Then L1 has a basis like this. L2 has a basis consisting of these commutators, and LCE has a basis IgG and IgK. Okay, and last example for today. Let K is say disjoint points, then LCRCK has a basis consisting of 5 commutators like this. Let we have one edge in this K, then LT has a basis consisting of 3 commutators like this. And let K has 2 edges, then LCE is generated by the commutator, one commutator, 1 CE. Okay, this is proof, sorry. And this paper with this result, and thank you for your attention.
Are there any questions or comments?
Look.
I have a little comment. Usually, Lie algebra in characteristic 2 needs supplementary conditions. If not, it will be completely commutative.
No, yep.
AB equal minus A.
Yeah. In over the 2, we have
2 and 3. It needs to be a supplementary condition. Yes, it's known question. You can see the algebra. Maybe more appropriate operation here is the classical ring.
Yeah. It's Ling. Yeah.
No, the algebra ring.
Over the 2, yeah, it's Ling because we have AB plus BA. Yeah.
A equals 0. Instead of AB is minus B, you will write A.
Yeah.
Well, other questions?
I have a question or remark.
Это из Zoom, видимо.
Yeah, thank you. Please, a question from Zoom.
Some of your formulas that you make mainly before the definition of the main theorem or a little bit later reminded me the admissible elements when Shirshov constructed the basis of free algebra. Is it by chance or you use this Shirshov basis?
Yeah, basic in the
maybe before the main theorem when you defined the iterated Lie brackets. I saw that this is maybe exactly admissible elements of construction. Maybe some slides before.
We have Так, я вроде то вывел, то, что надо. А вот.
Не, на экран.
Так, они не видели экрана, что ли? все?
Не, все видели. Я там это-
Several slides before, please.
А вот вершина, вот он. Так. Я не знаю. Так, сейчас. One second. Technical problems. Может, вот так? Может, закрепить?
When you were showing us
Я ж
no,
Попробуй ответить.
showing us the iterated
Я
several,
не знаю, как ответить.
yeah,
Да.
just before when you have many, not just 3, but many iterated Lie brackets before.
Владимир Валентинович, можно
Ага.
по-русски? Докладчик не очень понимает вопрос.
Ага. Значит, некоторые формулы есть вот перед формулировкой, где много элементов произведений, итерированные скобки Ли. И там мне напомнило как раз вот эти вот условия, и меньше К, больше и так далее, это есть в точности условия допустимых элементов при построении Шершовым свободных Ли алгебр. Вот, вот, собственно, и вопрос. То есть, может быть, тут прямо есть где-то у вас свободные Ли алгебры, и можно сослаться на Шершова.
I know that we have result about Pantryagin algebras, Panov, Teo, Gorbachev, that they similarly result with these conditions, but for Pantryagin algebras for moment angle complex. This result of Panov, Teo, Gorbachev, but about Фаили algebras, now я точно не знаю, что сказать, вот так скажем.
Ну, это старая работа, это диссертация Шершова, когда он был аспирантом Куроша, это 50-е годы. Ну, ладно.
Thank you for comment.
Well, I'm sorry, we need to postpone the further discussion to some coffee breaks, and now we have a coffee break till 16:30.